So far, the beam elements that we have dealt with had the loads applied at the nodes. The truss elements, of course, had loads applied at the nodes as well. And we have not looked at the situation where the loads can be applied somewhere between the nodes, or you can have a distributed load like this applied. Okay, you have a distributed load. This is a truss element, maybe a distributed load applied all along the length. Now, in these cases, what do? The elements that you have formulated are formulated with no loads applied in between the nodes. So if you have to handle this situation, you have to somehow reduce this distributed load into loads applied at the nodes. And you can do that in two ways. You can do that in a consistent manner or in an ad hoc manner. Both work, and surprisingly ad hoc in the ad hoc load distribution sometimes work quite well. And for the consistent nodal loads, to calculate the consistent nodal loads, there are formal techniques which we will learn later in the course. But right now, let me give you a glimpse of how the consistent and the ad hoc system works. And let me also try to convince you that the ad hoc system is not always very bad. So in this case, there is a load, total load in the x direction of magnitude QL, and we can apportion it by as QL by 2 and QL by 2 at the two nodes. Why is this consistent? This is consistent in the sense that if you do this apportioning, then the reaction force due to the supports at the two ends are QL by 2, which is same as what you will get here. So at least the reaction forces at the two nodes you will get to be the same in both the problems, though the load distribution, this load distribution is obviously not same as this load distribution, but this is how a consistent scheme will work. Now, if I have this problem, this is another example where a concentrated load is applied somewhere in the middle, somewhere at a distance L by 3 from node number 1, and then you can apportion this load again as 2p by 3 and p by 3. This would also be a consistent system. This is a consistent apportioning of the load, because again the reaction forces would come out to be the same in the two problems, though bending moments, etc., in this beam may not be same as in this beam. Okay, now if we take this consistent thing forward to a beam element, let's say I have a beam element which has now a transverse load, constant transverse load applied. Now if I can do one thing, I can try to formulate a beam element with this Q built in. So to do that, I will have to remember I solved this with 0 on the right hand side. Now I solve it with Q, and if I do that, then at both ends, if the beam is built in at both ends, I see that the bending moment and the shear forces will be obtained from the solution to this equation. I can solve this equation and I can find the bending moment and shear force. Remember, shear force is this at XL equal to 0 will give me V at XL, and then this at XL equal to 0 will give me M at XL. I can find V and M at this node, and then again I can repeat that for XL equal to L and find at this node. So if I find it, when I find it, I see that the shear forces are minus QL by 2 at the two nodes, and the bending moments are QL squared by 12 and minus QL squared by 12 and plus QL squared by 12 at the two nodes. So if I now want to replace, if I now say that I'm going to use my old beam element where I had derived the stiffness with this equal to 0, and still apply equivalent consistent load for this distributed system of load, then I will have to apply a moment of QL by 2 and shear force of QL by 2, QL by 2 at the two nodes, and plus and minus QL square by 12 moments at the two nodes. So this would be a consistent equivalent um, problem where I'm using a beam element with no transverse uh, beam element with a stiffness matrix that was derived for no transverse loads. I'm using that which I derived earlier and applying these loads to compensate for the distributed load that I have in the actual problem. So I'm solving this actual problem with a set of consistent loads but no transverse load applied. Again, the reaction forces are correctly represented in the original problem, which is this, and the problem with the consistent nodal loads. So the reaction forces are taken care of, though the solution may be different in the two cases. So this is how consistent nodal loads are obtained, and we keep on using elements that we have derived with some somewhat simplified assumptions, and the concentrated consistent loads are um, used to model more complicated problems with more difficult loading situations. Now, this is the consistent nodal loads. This is a set of consistent nodal loads for this element. What happens if I just ignore these guys? I just ignore these guys and use this ad hoc simplification. Now, this ad hoc actually completely ignores the bending moments at the ends, and therefore the reaction forces are not properly represented in this case. However, if I start using more and more number of elements in this region, I will see that this is not such a bad assumption. I will just give you an example. So let us say I am modeling this problem where I have a load of W applied uniformly across the B. Now, if I now use two elements to solve this, I have a node here, so this is my first element, node here, I have a second element. So what I will do is I'm now going to do an ad hoc apportioning of the nodes in the manner of this. So I'm going to take care of only the shear forces. I'm going to ignore the bending moments at the nodes completely. So what I'm going to do is I'm going to for this element, I'm going to put W L by 4, W L by 4. So this is L by 2, this is L by 2. So this load on the first element, element number 1, and this is element number 2. Let's node number 1, 2, and 3. So for element number 1, I will put WL by 4 here and WL by 4 here. For element number 2, I will put WL by 4 here and WL by 4 here. So in the global force vector, I will have WL by 4, WL by 2, and WL by 4 as my nodal loads for a system which has been discretized into two elements with ad hoc apportioning of the distributed load. So this is what I have actually modeled to model this distributed loading system. And if you see the shear force diagram of this, the bending moment diagram of the actual situation is this. So at the location of node number 2, you have a bending moment of WL square by 8. In this problem, however, this is your shear force diagram. So this is WL by 4. This is a drop of WL by 2, and this is WL by 4 again. And here, this bending moment is this area. So WL by 4. So this is WL square by 8. So this bending moment is correctly represented at this point, but the distribution of the bending moment in this region, and in this region, it's a curved quadratic curve here, but here it's a linear bending moment. So obviously you are not getting the bending moment right, but you're getting the bending moment right at the middle, but you're not getting it right anywhere else. you are getting it right at the ends as well, but you are not getting it right anywhere in between. Now, assume that I break up this. So this is, of course, the result of the ad hoc apportioning of this distributed load. Now, this you feel is probably not good. Uh, so let us break it up into more elements. So put nodes here, nodes here. So I have element 1, 2, 3, and 4 now. And now how am I going to apportion the loads? So I have 1, 2, 3, 4 elements. So WL by 8 goes, for the first element I'll have WL by 8, WL by 8. For the second element I'll have WL by 8 and WL by 8. So this will become WL by 4. From the third element, I'll have WL by 8, WL by 8. This will become WL by 4 again, and this will become WL by 4, and the corner one will have WL by 8. So now, if you draw the shear force diagram of this is how the shear force diagram is going to look like, and this is how the bending moment diagram is going to look. And you see that you still have linear variations which doesn't match with the actual quadratic one, but the gaps have reduced because you are now matching the solution at all these points, matching the exact bending moment at all these points, though here you have less amount of error than this. So the ad hoc apportioning of loads is working when you increase the number of elements. If you now halve every element, and you will have WL by 16 on the left, WL by 16 on the right, and WL by 8 at the intermediate nodes. And then in that case, you will get even closer to the actual bending moment diagram. So the point that I wanted to make is that ad hoc apportioning of loads may actually be a good policy when you are using um, many number of elements. You can still get close to the correct solution. Let's stop here for this week.